So remembering back to fluids again, remember what our definition of Reynolds number is. The Reynolds number is, it's that ratio, but specifically it's saying rho times u infinity times some characteristic length, let's call this L characteristic, divided by mu. This is just the definition of Reynolds number. This characteristic length is something that we have to decide, right? We have to use our judgment to decide what is the relevant length for the Reynolds number that we care about. So if we look at flow over a flat plate, there's a specific Reynolds number for that. So we're looking at Reynolds number. The Reynolds number is going to be equal to rho times u infinity times the characteristic length. Well, we know that the heat transfer coefficient, the thing that we're computing, is depending on the coordinate x. So we actually care about x, the x position, the current position that we're inspecting, is our characteristic length. For other geometries like a cylinder or a triangle profile or something like that, the characteristic length is going to be different. For flow over a flat plate, it's x, right? So that's all divided by mu. And then we'll note that our Reynolds number is actually Reynolds number for some coordinate x. So we'll write it Rex, and often we're going to write the Reynolds number with a subscript here for the characteristic length that we're computing, just so we remember what it is that we're referring to. Okay, so that's our Reynolds number. So what we want to do is get the boundary layer in terms of the Reynolds number. Well, let's start with the momentum boundary layer. The momentum boundary layer is a little easier because it's relating only the velocity, the momentum components, and if you note up here, these are all velocity or momentum related. So our momentum boundary layer model was delta m. It's approximately equal to 2 square root of nu times x over u infinity. So let's do a little bit of manipulation to try to see if we can't pull a Reynolds number out of this expression. So let's convert this to something similar by dividing both sides by x. So delta m over x, and then 2 over x. Square root of nu of x over u infinity. So then the next step is let's bring this x over here inside the square root, and that's going to yield delta m over x is approximately equal to 2 the square root of nu over x times u infinity. Right, so it's equivalent, we're just sort of change things around. So remember also that this nu, the kinematic viscosity, is equal to the dynamic viscosity mu over rho. So we can substitute that in, and then we get delta m over x approximately equal to 2 square root of mu over x times u infinity times rho. So this quantity here is 1 over the Reynolds number. All right, 1 over the Reynolds number in terms of x. So actually our approximate model here for momentum boundary layer is delta m is approximately equal to 2 times x over the square root of the Reynolds number x. This approximate model is something you can use. It's with all the assumptions that we made, it's kind of a reasonable estimate of delta m, but it's not the most accurate version. So if we were to actually go through, apply a momentum velocity profile for our boundary layer, assume that profile all the way through, and then solve a differential equation, we would end up with something that's called a self-similar solution. And the self-similar solution is delta m is equal, so now we'll say it's exactly equal to 4.916 times x over Reynolds x to the 0.5, or square root of Reynolds x. So this is the model that you're going to want to use. right? This is the more accurate version. And you'll note that like the only difference is basically a factor of 4.916 over 2. So we are, with our really conceptual model, we got basically within a factor of 2 to 3 in terms of the boundary layer, which is actually, pretty good. But this is how we would estimate the momentum boundary layer. For the thermal boundary layer, we can do something similar. I'm not going to do the full derivation, but we would end up with something like this. We'd say delta T is approximately equal to 2x over the square root of Reynolds x times the Prandtl number. And so the Prandtl number now appears, and that makes sense because there's a relationship between delta T and delta M, and that's the Prandtl number. The exact model for this is again 4.916 times x over Reynolds x to the 0.5 times the Prandtl number to not the 0.5, but actually the 0.33, or 1/3. So this is now our exact model for the boundary layer thickness for the thermal part of the problem. The boundary layer thicknesses that we're computing, these are dimensional values. These are things with units like meters. And often we're wanting to express heat transfer, shear stress in terms of these non-dimensional coefficients. So instead of saying my heat transfer coefficient is related to some specific dimensions, we can represent it in terms of a non-dimensionalized problem so that we can extend it to other geometries and other situations really easily. So let's go through some quick derivations here that help us relate both the shear stress and the heat transfer coefficient to equivalent non-dimensional quantities that we'll use for like correlations and things like that. So our non-dimensional expressions for tau and hx, let's start with tau. So the definition of shear stress in terms of the friction coefficient, which you probably remember from fluids, is shear stress is equal to 1/2 rho u infinity squared times CF. So the first thing to point out is this is just the momentum, right? This is just the momentum of the fluid, rho u squared over 2. So we're relating the momentum of the fluid times some coefficient gives us a shear stress. So let's use this conceptual model where we said tau is approximately equal to this is mu, the viscosity, times u infinity over delta m, where delta m is approximately equal to, let's use our approximate model, 2x over the square root of Reynolds number. So using these, we can say now CF is approximately equal to 2 mu over rho u infinity delta m. Okay, so with this, we can go back and combine these equations, or combine this model, and we're going to say CF is approximately equal to 2 mu over rho u infinity. Now we have to add in this delta m part of it. So delta m was 2x over square root of Reynolds, so this is square root of Reynolds x over 2x. All right, so now we can just do some kind of minor rearrangements. So this is CF is approximately mu over rho u infinity x times the square root of Reynolds x. And if you look carefully, this is again 1 over Reynolds number. So from this model, we actually see CF is approximately equal to 1 over the square root of Reynolds. Our exact model, so this is approximate. If you go through the same type of analysis but using exact solutions, we would get the exact model CF equals 0.664 over the square root of the Reynolds number. This you should probably recognize, right? This is from fluids. This would be like that the laminar flow friction coefficient that you would see in like the Moody diagram. We can do the same type of analysis again for the heat transfer coefficient. And instead of the friction coefficient goes with the shear stress, for heat transfer coefficient, we end up with something called a Nusselt number. Nusselt number is just a non-dimensional heat transfer, non-dimensional heat transfer coefficient. So the definition of Nusselt is the following. It is Nusselt, which is at a particular coordinate x, is equal to the heat transfer coefficient x times the position x over k. Right? This is for flow over a flat plate. Now, since we remember that h is approximately equal to k over delta t, then we can substitute that in, and we can get delta t is approximately equal to, before we substitute that in, also note delta t is approximately equal to 2x over square root of Reynolds times square root of Prandtl. This is from the previous slide, just the approximate model we developed. So we're using this approximation and we're using this approximation together. So combining those, we get x over Nusselt x is approximately equal to 2x over square root of Reynolds Prandtl. Solving this for Nusselt number, we get Nusselt x is approximately equal to 1/2 square root Reynolds Prandtl. Again, our approximate model. The exact model is as follows. It is Nusselt x is equal to 0.332 times Reynolds to the 0.5 times Prandtl to the 0.33. And again, this is all for flow over a flat plate. So we now have these non-dimensional quantities, friction coefficient, Nusselt number, and eventually, like I said, we're probably going to want to plug these into a correlation and express them that way.